Welcome to The Explainer. So let's dive right into this. You know, when you're scrolling through the news and you see one of those flashy medical headlines and you just kind of wonder, is that actually true? Or is there something hiding beneath all those numbers? Well, today we're going to act as statistical detectives. Our mission? To track down the truth hidden within messy, real world medical data. We're going to explore exactly how investigators take observational data, where treatments aren't just neatly and randomly assigned, and figure out how to separate absolute fact from statistical fiction. Let's kick things off with a classic epidemiological riddle. Does coffee cause lung cancer? I mean, it sounds completely absurd, right? No way. But here's the thing. If you were to just glance at a raw set of observational data, you might actually see a massive correlation. You'd see a whole lot of heavy coffee drinkers getting lung cancer, and you might naturally assume one just causes the other. This right here is the exact illusion of a false conclusion that our statistical detectives are hired to solve. So the absolutely crucial point is understanding why that correlation is popping up in the first place. Enter our true culprit, the confounding variable. A confounder is basically an external third variable that is secretly related to both the exposure, which is coffee in this case, and the outcome, lung cancer. It creates this wild illusion of causality where none actually exists. In our coffee mystery, that hidden variable is smoking. This beautifully illustrates how those sneaky third variables completely distort reality. If folks who happen to drink a ton of coffee also tend to smoke more cigarettes, and we know for a fact smoking causes lung cancer, then suddenly coffee falsely looks like the bad guy. That smoking variable heavily muddies the observational data. So the big question for researchers is, how on earth do we neutralize this? Well, let's look at how we'd ideally fix it. Section 1, the gold standard, randomization. Traditionally, medical researchers love to level the playing field to ensure a strictly fair fight between their study groups. And that is the sheer unmatched power of randomization. A true randomized controlled trial, or RCT, is the gold standard of medical research. Why? Precisely because randomly assigning patients inherently creates prognostic balance. It acts literally like a magic wand that evenly distributes every single variable between the groups. We're talking about both the confounders we know about, like age and smoking status, and the completely unknown confounders we haven't even discovered yet. Randomization just magically neutralizes them all. But, here is the real-world dilemma. What if we simply can't randomize? Think about it. You can't just force a random group of totally healthy people to smoke cigarettes just to see what happens to their lungs. It's unethical. Or sometimes it's just physically, practically, or financially impossible to run a massive trial. In those situations, investigators are forced to rely on messy observational data, and they have to roll up their sleeves and clean it up themselves. Which brings us to the first really powerful tool in our statistical toolkit. Section 2, Tool 1, Design Stage Matching. This is a highly sophisticated strategy that researchers execute right at the design stage of a study, completely before any outcomes are ever even compared. The goal here is to physically mimic the structure of a randomized trial. Let's walk through exactly how this comes together. First, researchers look at a patient's baseline characteristics, things like their age, sex, and existing comorbidities. They feed all of this into an algorithm to calculate a single probability score, known as a propensity score, ranging from 0 to 1. Think of it like a statistical fingerprint. It represents the likelihood that the specific patient would receive the treatment based purely on their baseline profile. Step 2. The investigator physically pairs each treated patient with an untreated patient who possesses an identical or nearly identical propensity score. Finally, and this is a big deal, they discard any unmatched patients. By matching individuals up this way, they assemble two distinct cohorts that are perfectly structurally balanced across all measured baseline characteristics. In real-world applications, the takeaway is crystal clear. Matching participants by a known confounder, like age, transparently decreases the chance for confounding. By actively, physically matching patients based on these characteristics right at the inception of the study, researchers successfully mimic the configuration of a randomized controlled trial within a data set that was never actually randomized in the first place. Pretty brilliant, right? But matching isn't our only option. Let's fast forward in the study lifecycle. Section 3, Tool 2, Analysis Stage Multivariable Regression. This second major tool fixes imbalances after all the data has already been completely collected. Instead of physically pairing up individual patients or altering who's in the study groups, multivariable regression uses sophisticated statistical software. It builds a massive, comprehensive mathematical model that includes both the primary exposure and all the suspected confounding variables as independent predictors within a single equation. Basically, the software figures out the independent effect of the primary exposure on the outcome while mathematically holding all those other included variables constant. Think of it kind of like a referee using math to adjust the scorecards after the game has already been played. Now, choosing between these two sophisticated methods requires researchers to make a pretty major operational choice. Section 4, the trade-off, power versus transparency. As they say, you can't have your cake and eat it too. This sharply contrasts our two statistical techniques. On one side, we have matching. It happens right at the design stage and gives us beautifully, transparently balanced groups, but it forces us to drop unmatched patients. On the flip side, we have multivariable regression. It happens at the analysis stage and mathematically adjusts the data, which is awesome because it allows it to utilize the full, untouched data set. Let's really break down the exact consequences of that trade-off. Check out the sample size. With propensity matching, because you literally discard unmatched patients, your sample size inherently shrinks, and that directly reduces your statistical power. Multivariable regression, on the other hand, preserves the full data set. That provides a massive operational advantage by maximizing power. But wait, look at the risk of modeling error. Matching is highly transparent. Regression, however, relies entirely on the assumption that the mathematical relationship between the variables is perfectly specified. If the true biological relationship is nonlinear, while regression models are suddenly highly vulnerable to modeling errors. So why do we care so much about statistical power anyway? Well, simply put, increasing the power of a study through larger sample sizes decreases the incidence of a type 2 error. A type 2 error is essentially a false negative. It's when a study totally misses a real effect and concludes there's no difference, when in fact a true difference really exists. When a researcher's top operational priority is preventing a type 2 error and maximizing that sample size, multivariable regression is absolutely going to be their go-to choice. Okay, prepare yourselves for a dramatic plot twist. Section 5, the ultimate limitation, unmeasured confounders. No matter how incredibly brilliant our statistical detectives are, there is a shared vulnerability that constantly threatens both of our tools. I want you to just pause and ponder this for a second. What if we missed something? What if there is a variable out there that is fundamentally altering the outcomes, but the researchers completely forgot to write it down? That single question builds into a massive headache for researchers. These are the invisible factors that slip right past all our fancy statistical defenses. We're talking about unrecorded dietary habits, or maybe subclinical genetic variants that haven't even been discovered by science yet. What about undocumented environmental exposures at a patient's workplace? These invisible variables might heavily influence both the treatment choice and the final outcome, and we'd be completely blind to them. And that is the absolute ultimate limitation of observational data. Unlike a true randomized controlled trial, which magically balances out the unknown, neither propensity score matching nor multivariable regression can account for variables that were never recorded. If an unmeasured factor is heavily associated with both the treatment choice and the outcome, both of these mathematical techniques are going to fail. They will produce an adjusted estimate that remains heavily biased. So let's summarize the final takeaway for all you clinicians and researchers trying to navigate this complex landscape. If you've got a massive data set and you want highly comparable, transparently balanced treatment groups, neutralize your confounding at the design stage using propensity score matching. But if preserving statistical power and maximizing your total sample size is your main operational priority, neutralize it at the analysis stage with multivariable regression. Just remember the golden rule. Neither tool can save you from what you forgot to measure. Which leaves us with one final thought. The very next time you are scrolling through your feed and you read a groundbreaking medical headline based on observational data, I want you to stop, look really closely at the claim, and ask yourself, what invisible variable did the statistical detectives forget to measure? Thanks so much for joining me on this explainer, and stay curious.